Jai Hind to all. My name is Dhanshri Parihar, Assistant Professor, Department of Computer Science and Engineering, Ajay Kumar Garg Engineering College. Today, my topic is virtual memory from the subject Computer Organization and Architecture. So the overview of the content includes introduction to virtual memory, paging and segmentation, introduction to page replacement algorithms and strategies, FIFO page replacement algorithm, LRU page replacement algorithm, and optimal page replacement algorithm. So what is virtual memory? A virtual memory is a program that will give an illusion to a programmer that the system has a very large memory, even though the computer actually has a relatively very small main memory. That is, we are talking about the RAM memory, random access memory. So we are having two addresses. One is the virtual address in this case, and one is the physical address. Physical address is the address which is being issued by the central processing unit, that is by the processor. The virtual address is the address where we can find our virtual memory. So this physical address is known as a memory space in a computer system, and this virtual address is known as an address space in a computer system. Here the address are generated by the programmer itself, and it will reside in the actual memory, the physical address in a RAM memory. So the address mapping, in an address mapping scheme, what we will do for utilizing the virtual memory, we have to convert this virtual address to physical address. And how that will be possible? By using this logic. First of all, the virtual address that is being issued by the CPU is loaded into a virtual address register. Okay, that is an address register. And then a memory mapping table is used where we are storing the page number and their presence bit in respective to that. After that, that particular page is loaded in a memory table buffer register. And after that, a physical address is constructed from the virtual address and being loaded into a main memory address register. After that, when we get this address of the content of the main memory, that is RAM, we will go to the main memory where we find out our block which we want to access. And after that, we will be having a main memory buffer register where we can have the data which is being accessed from the RAM memory. So let us take an example how this procedure can be possible. So in this example, we are taking an address space and a memory space, that is a virtual memory address space and a memory space for your RAM memory, and we are dividing them into a fixed size of groups which are known as the blocks and pages. So the contents of main memory are known as blocks, and here in this example we are taking a main memory of size 4K, and the pages are the contents of virtual memory, and here we are taking a virtual memory to be size of 8K. Now we are converting the K, that is the unit, into 2 raised power 13. How it is possible? 2 raised power 3 is for 8 into 2 raised power 10 to convert the kilobyte to byte. Okay, and when we will get 2 raised power 13 as a complete, we can say, the address space for this. So we are, in this example, we are taking the virtual memory of size 8K. So, and each page is of size 1 kilobyte. Here it is given 1 kilobyte. So page 0, 1, 2, 3, 4, 5, 6 and 7. 0 to 8 pages. Each page of 1 kilobyte. And a memory block. So here we are taking memory of size 4K, that is kilobyte. That is block 0, 1, 2, 3, 4. Okay. And one block will be of 1K size. Now how this particular mapping will be possible, that is virtual memory is being mapped into your main memory, and how a page is used to access a block in a main memory. So let us consider example that a virtual address is given to us. Here it will be of 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12, 13 bit. So 13 bit virtual address is given to us. Okay, and it will be issued by our computer system, operating system it is being issued by. It is divided into two parts. One is the page number and one is your line number. This whole technique of mapping a virtual address to our physical address is known as paging technique. Okay, so the first 3 bits are page number and the last 10 bits are line number. Okay, so 101, here we are having different addresses of the pages 000, 001, 010 in a sequence of this. Okay, from 0 to our 7, like this, 0 to 7, binary code of all this. And here we are having some value stored in these particular addresses like 110001 and 100. These are actually the page number. Page number 11, page number 0, that is page 0, page 11, page 7, 01, page 1, and 10, page number 2. Okay, and these are corresponding presence bit. What are presence bit? If the page will be available in the memory, then the presence bit value will be 1, showing its presence in the virtual memory, and its value will be 0 if it is not present in the virtual memory. So we are having 4 pages residing in this mapping table, 1, 2, 3, 4, and their corresponding presence bits are 1, 1, 1, 1. That means these locations are filled by some pages, and other locations which are having corresponding bit to be 0 are empty. Now, what we have to do, since we are having page number 101, we will go to 101 location. This is the page number. Its corresponding block is 01 and it is present in the memory. We will copy that into this physical address and then its presence bits also. Okay, and then after that it will be then stored in this memory, main memory address register, where the value 01 will be stored and corresponding line number will be copied from this virtual memory. Okay, now from here further we will go to main memory, where we will search for block 01. This is the location of actually the block that the page is going to be mapped in the main memory. So 01 is the page number, block number 1 in the main memory. As block 1 will be having a binary value of 01. This will be your 10. This is 11 and this is your 00. So at 01 location we are having block number 1. And what are these? These are actually the line. We can say the address of word inside your block which we want to access. At block number 1 we can access the word or some contents with this particular address of line. Okay, and after that when the block is being accessed, the data is being transmitted to memory buffer register. So this is the process known as a paging process for implementing the concept of virtual memory and mapping a virtual address to a physical address that we can access from your RAM memory. So virtual memory is a kind of a illusion to the programmer that a very wide space of memory is available, wide space of physical memory is available to the programmer or to the user. But in reality it is not there. Okay, it is extension of RAM plus your hard disk. That is the concept of virtual memory. Now, next is we are talking about the concept of page replacement algorithm. There is another technique which is known as segmentation that can be used for implementing our virtual memory. Okay, and now these are the page replacement algorithm. What are these page replacement algorithm? Whenever this page is inside the memory, okay, this page is inside the memory and we want to replace these pages in a virtual memory by some other page, we need some replacement strategy which is known as page replacement algorithm. Since your virtual memory is of some fixed size and we can accommodate only 7 pages in this case, 8 pages in this case. So whenever some page need to be replaced or data is not found in the virtual memory, we need to replace it by some another page. For that we need a page replacement algorithm strategy. Okay, so that is the page replacement. That is the decision on which the pages need to be displayed from your virtual memory to make a room for incoming page when no free frame is available. Okay, and how it can be done? We have to find the location of the desired page on a backing store, either looking into the past or looking into the present. Okay, if there is some free frame, then we have to use it. Otherwise, use a page replacement algorithm. Okay, if we are having some free space in the memory, then we have can use it and occupied it. But if all the contents of virtual memory are occupied, then we need to replace it by using your page replacement algorithm. And we have to select that victim frame where we have to perform that replacement strategy. Okay, so how it is possible? So we are having different algorithms for them. That is the different strategy. The first page replacement strategy is FIFO, first in first out page replacement algorithm. So let us take a help of an example to get into it, how this page replacement strategy is possible. As the name suggests, it is a first in first out page replacement. So we are following this concept of whatever page will be inserted first into this virtual memory will be the first one to be moved out from the virtual memory. So that is the basic concept of using this algorithm. So let us take an example of this string. We are having some elements in the string like this 7012030430321201701 random string. Okay, and let us consider that a page frame, that is a virtual memory of size of 3K, or we can say 3 pages. Okay, so we are having 3 frames, or we can say 3 pages in the virtual memory. So first of all, insert 7 into this first insertion. Then we have 0 in the string, insert 0. Then we have 1 in the string, we will be inserting 1. Okay, 7 will be the first one to enter into the memory, 0 will be the next one to enter into the memory, and 1 will be the next one to at third location. Now our memory is now occupied and we will got 701 in our frame. Now what will happen if the 2 wants to come into this memory? So we have already 3 locations occupied by 701, 3 values. So what we have to use? We have to use the concept of first in first out order on this particular memory. So 2 will be replacing 7. Why it will be replacing 7? Because 7 will be the first one to enter into our this virtual memory. So 7 will be being replaced by 2 and we will get 201. Okay, that is this previous memory will be updated now. Next value will be the 0. Okay, and the 0 will automatically previously present in this virtual memory. So there is no need of replacing 0 from the memory. Okay, the next is 3. Again we have 2, 0 and 1. So out of these 3 value, which one will be replaced? 0 will be replaced. Why? Because 0 will be the second value to enter into our this virtual memory. Okay, so 0 is being replaced by 3. Now next value is 0. For 0, because previous 0 is being replaced, now we will be having 2, 3 and 0. This 1 is being replaced by the 0 again. Previously 0 was present, but it has been removed from the memory. So we need to insert it again into the memory, and for that insertion process we need to follow FIFO order again. Okay, and in this case 2 and 3 already replaced. Now we have third value 1, which is entered third in our this frame. So 0 is replacing this 1 from the memory and we will get 2, 3 and 0. Next element is 4. 4 is replacing 2 because 2 is the next one to enter in the memory. Okay, 4, 3, 0 and 2. Again 3 will be replaced by the 2. Then we have 3. Then 0 will be replaced by 3 and so on. And this process will follow till we reach the end of this string which is given us to process to be inserted into our this virtual memory. Okay, so in this first in first out algorithm, the number of steps we will follow, that is very large. That is one of the drawback of using this first in first out page replacement algorithm. Okay, but the advantage is this strategy is very easy to implement, and here another problem is it will result in a very frequent page fault. So page fault ratio is very high in this strategy. Okay, so that's why we need some another algorithm to overcome its drawback. After this we have LRU, that is least recently used page replacement algorithm. So it will follow the principle of replacing that page which has not been used for the longest period of time. So in LRU strategy, we may require substantial hardware resistance, and the problem is to determine order of the frames, define the time of last use. So in this strategy, we will look into the past, into the string, how many times that element is being used in the past. On the basis of that, the replacement will be occurred. So let us have a look with this example, how this is possible, the longest period of time, how it is checked from the past. Okay, same we have done in this FIFO. Insert 7, then insert 0, and then 1. We have 3 frames in our this virtual memory. Okay, now when the 2 will come, out of 3, which will need to be replaced? So we will look back into the past from the 2. So which one is the farthest from this 2? That is, which is not being used for the long time. If we see 1, that is most recently close to your 2 and is used recently. 0 is also recently used, but 7 is 2 step, we can say, far away from our 2. So it is the element which is not being used recently. It is the longest in a time from the element number 2. So that's why we are replacing 7 and we are having 2, 0 and 1. So 7 is replaced by 2. Now next element is 0, which is automatically already present in your memory. So this will hit in our this particular page replacement algorithm. In this we can say virtual memory. Whenever the page is not found in the memory, it is a, we can say, page fault. Okay, and whenever it is found in the virtual memory, it is known as a page hit. Now next element is 3. So out of 2, 0 and 1, 3 is going to replace which element? So we will again look into the past. 0 is closest to 3, so 0 cannot be replaced. Then we have 2, 2 also cannot be replaced. Why? Because 2 is also nearest to. Then we have 1. So 1 is farthest from 3. So that's why 1 will be replaced. Okay, so this 1 will be replaced and here we will insert 3 in place of 1. Similarly, we will proceed with the further string. Now again we have 0. 0 is already in the memory. We have a page hit. Then we have a 4. 4 need to be checked in its past. Which one is far away? 0 is nearest. 0 cannot be replaced. Then 4 is farther. So 4 के पीछे means 2 is there. 4 के बाद है 3. This is 3. Again 3 cannot be replaced. Then we have 2, which is farthest from the 4. So we need to replace this 2 and we will insert the 4 over here. And so on, we will follow the same process. Now what will happen if the value which is present in this virtual memory is not present in the past? Okay, suppose we are having this 402 and we need to insert this 2 into the memory, and whatever we are looking at the back, okay, which is present in the memory, like we have this 402, okay, this 403, and this 0 is never lying in the past. Some element which is in the memory or which is in the string and cannot lie in the past, what will happen? So in that case, if we do not find element in the past, we will be using first in first out strategy, which is a tiebreaker for this algorithm. Else we will follow the same strategy to looking in the past, and if the element is not present in the past, we will be taking first in first out strategy for that. Okay, so and so on, we will getting the same criteria. We will follow the string till the string will end. So this is the least recently used page replacement algorithm. Again, it will be having some drawback here, since we are having a substitution hardware resistance we need. So that is one of the drawback of using this LRU strategy. And for improving it, we have another algorithm which is known as optimal page replacement algorithm. In optimal page replacement algorithm, the pages are replaced which would not be used for the longest duration of time in the future. Now in previously, in LRU, we will be looking at the back, but in optimal page replacement algorithm, we will access the future string. So one of the drawback of optimal page replacement algorithm is we need to know the complete string in advance whenever we used to implement this algorithm. Okay, so we need to have the knowledge of that particular string in advance. If we do not, if we want it to run dynamically for a dynamic string, it is not that much possible. Okay, so let us consider an example of the string 701203042303323. Okay, and now what we have to do, we have to insert the elements into this string. We are inserting 7. Here in this example, they're performing the insertion from the end of the block. We can insert the element from the top also and from the bottom, but we can use only one direction for that insertion. Okay, so we are having this 7 inserted, then we have 0, and here the number of frames in the virtual memory is of size 4. Okay, we are having 4 frames. So 7 0, then we have 1, then we have 2. Okay, 7 0 1 and 2. Now our memory is completely filled. What will happen when we want to insert this 0? Since this 0 is already in the line the virtual memory, so it is a page hit. Now next is 3. Now we want to insert 3 into this. So which element is going to be replaced? 2, 1, 0 or 3? That will be depend upon looking into the future. So this is the location of 3, and we'll perform a seek at in the future. So this 0 is the nearest element, 4 is again the nearest element. So what we are having in this, we have 0, okay, then we have 4 doesn't exist in the string, then we have 2, 0 and 2, then again 3, then we have 0, then again 3, then 2. So we have a choice among 1 and 7. So out of 1 and 7, anyone we can replace, but here we will use first in first out strategy for that purpose. Okay, so out of 1 and 7, which will be inserted first? I think that will be 7. That's why we have replaced 3. Here the 7 is the first element to be entered into our virtual memory. That's why the 7 is being removed, not the 1. As although 1 is also not present in future and 7 is not present in the future, so any one of them can be replaced. But we are using a page replacement strategy here to decide among 1 or 7 which one have to be removed. Now next is when we insert the 3 in place of 7, again we have 0 in the string already present, we have a hit. Whenever the page is not found, it is a miss, and whenever it is present in the memory, it is a hit. Now next is 2 is already in the memory, 3 is already in the memory, 0 again hit it, and we got this hit when we are accessing the further. Okay, so the number of page faults are 6. So here the number of page fault and hits will decide the our replacement algorithm accuracy, in how minimum we can say duration we can utilize this page replacement. So that is all about optimal page replacement algorithm. Thank you and Jai Hind to all.